Alright, next we're going to talk about angular kinematics. So, you might recognize these three equations. They're kind of the three that we use the most. There was actually two other kinematics equations, but I'm just going to focus on these right now. We worked on these in the second chapter and the third and fourth chapter when we talked about constant acceleration. And so these are constant acceleration equations, our kinematics equations, and we can actually use these exact same equations to talk about angular kinematics. So relating angular displacements with angular velocities and so on. Now, the reason why this works is because the whole principle of these equations is that you have a constant acceleration, okay? And all of these are pretty closely related through calculus, through derivatives, especially, well, these two especially are related because if you take the derivative of this equation with respect to time, you actually get that one. This one, there's a little more algebra involved, but all of it has to do with the fact that acceleration is constant. And so when we have constant acceleration for angular quantities, the same thing applies. The angular velocity is equal to the initial angular velocity plus angular acceleration times time. We have our angular displacement is equal to our initial angular velocity times time plus 1/2 times alpha t squared, and so on. We get our final angular velocity squared equal to initial angular velocity squared plus 2 times alpha times delta x. So kind of the trick here is being able to switch back and forth between, realize you're using the same equation, it's just that these are angular quantities, and recognizing that, like, alpha, for example, is the angular counterpart to a for acceleration, and so on. And so we're going to go ahead and try these out in some problem-solving settings and see how we do. Alright, so here we have a situation. This would be a grindstone. It's got this reference line right here, and we're saying that at time 0 it has angular velocity of negative 4.6 radians per second. If it has a negative velocity, that means it's going which way? It would be clockwise. So omega naught is equal to negative 4.6. These are radians per second. We have an acceleration of 0.35 radians per second squared, and we're going to say our initial position, so this starting position we'll call 0. Okay, and that's just going to mean that whatever our position is would be equivalent to our displacement. So it says after what time t equals 0 is the reference line at the angular position of theta equals 5 revolutions. Now before we continue, when we talk about rotational motion, one of the things that happens is we have to do things like give time references because these patterns are very cyclical, and so we're going to say we're starting from t equals 0. I don't know why we do it this way. It's just kind of one of those things that you do. So in this chapter, a lot of times we're going to reference when, like, the time that's starting from. So we're going to be kind of counting the passage of time, or the change in time. So anyways, we have a position of 5 revolutions, which if we want to convert that to radians, that would be 2 pi times 5, okay, giving us 10 pi radians. Okay, so we want to know at what time do we get 10 pi radians given our initial velocity and our acceleration. Okay, so with those quantities, it makes me want to use this equation, right? Omega naught t plus 1/2 alpha t squared. Okay, and so we're going to put in 10 pi here for theta. This is going to be negative 4.6 radians per second times t plus 1/2 times 0.35 radians per second times t squared. Okay, we'll subtract the 10 pi over, So 0 equals negative 4.6t plus 1/2 times 0.35 would be 0.175, and this is times t squared. These, by the way, are radians per second squared. Okay, oh, and then minus 10 pi, 10 times 3.14 would be 31.4. Okay, now from here we have t there, we have t squared there. So we're going to go ahead and punch this into the quadratic solver app on my phone and see what we get. This would be A, B, and C. So we solve this and we get that t is equal to negative 5.6 seconds and 31.9 seconds. Okay, so we have to decide, well, which one should it be? Well, it says very clearly here that at what time after what time t equals 0. So this one would come before, so our answer here, 31.9 seconds. Alright, we get to the second part here. It says write expressions for the angular position and angular velocity with respect to time. We're going to come back to this right here, okay, and just plug in some values into here. So showing the relationship between angular position and time. So we're going to input our starting velocity and our acceleration. I simplified it here, so I'm going to come back to this right here. So the 0.175 t squared. And so now we have a function relating position and time. Okay, so that would be one of your answers. For the second one, it's asking for angular velocity, so we'll use this equation right here. Alright, and we'll substitute these two values that we know, and we'll leave these two as variables. So omega equals negative 4.6 plus 0.35 t. Okay, so now we have an expression for angular velocity with respect to time and angular position with respect to time. Okay, the last part says at what time t does the grindstone momentarily stop? Well, that would be at what time is the velocity equal to 0. So we can take this equation right here. We can substitute 0 for our final velocity. 0 equals negative 4.6 plus 0.35 t. Do a little bit of algebra, and t will be equal to 4.6 over 0.35. Okay. You divide those and you get that it would take 16 seconds for it to come to a stop. Okay, and then after that point, it would turn around and go in the positive direction. Okay, and then somehow after 32 seconds, it will have completed 5 revolutions. Doesn't really make sense to me, but anyway, I hope you kind of get the idea of using these kinematics equations here. Okay, I want to also look at this checkpoint real quick. You saw this in the book as well. It says, to which situations do the constant angular acceleration equations apply? So that'd be situations where you have a constant acceleration. Okay, if you look at these, that would be situations where the second derivative is constant. So let's start by looking at this one. Okay, this is linear, which means that the second derivative would be equal to 0, which means that that would work for those constant acceleration equations. So that one. This one is cubed, so that means that the second derivative would be linear, which means it doesn't work here because it needs to be constant. For this one, it's an inverse square function, which means that the second derivative would be over t to the 4th, which wouldn't work for us. And then finally here we have 5t squared. Second derivative of that would be 10, and so we're good with that one too. So it works for both A and D. Alright, so last one we're going to do, we're operating a ride called the rotor, in which people spin around in circles really fast. And we see a passenger in distress. Probably they're starting to feel a little bit sick. And so we're going to slow down from 3.4 radians per second to 2 radians per second, and we're going to do it, and throughout that time, while it's slowing down, it's going to go actually travel 20 revolutions before it slows that down that much. So it asks about what the angular acceleration is. So what is alpha? We're given an initial angular velocity of 3.4 radians per second, a final angular velocity of 2 radians per second, and an angular displacement of 20 revolutions, or 40 pi radians. Okay, so we have 1, 2, 3, 4 quantities they want to compare. We're going to use this equation right here because it has all 4 of them in it. Okay, oops, wrong variable there. Okay, we're solving for alpha. Okay, so we're going to say 2 squared equals 3.4 squared plus 2 alpha times 40 pi. Okay, and let's go ahead and do this calculation. Okay, so anyway, starting to simplify, and as we get to the end, we get that we're going to end up dividing 7.56 by 251.2, and we get that alpha is about negative 0.03 radians per second squared, which is a really small angular acceleration. Okay, which if you look here, it spun up a whole bunch of times before it got to that final velocity. Which, kind of in the context of this problem, clearly this ride operator doesn't really care about the passenger that much because they're not really slowing it down at much of any kind of urgent rate there. So anyway, we can go ahead and find out how much time that took. Okay, using that, we'll use this equation right here. Alright, so we have 2 for our final, 3.4 for our initial, and our negative acceleration. Okay, and we're going to find that it's going to take about 47 seconds. Okay, and so that's a really long time, especially if someone's feeling sick or whatever that's going on there. Anyway, it asks for the change in centripetal acceleration. So we've been talking about tangential acceleration, and when we talk about the linear quantities, we want the centripetal one. So this is the circle. We want to look at this, which, if you remember, is v squared over r. Or, if you remember that v is equal to omega r, then it is equal to omega r squared over r, or omega squared r. Okay, so we're going to find the change in omega squared r. So that would be omega squared r minus omega initial squared r. And so we get 2 times, so 2 squared times our radius of 8 meters minus 3.4 squared times 8. Okay, so we substitute in the values, we simplify, and we find that we have a change in centripetal acceleration of negative 60, and these would be meters per second squared. Okay, so before we finish here, I just want to mention centripetal acceleration is basically what you would feel if you were riding this ride. Like, it would kind of be the strength. And so we started with, or rather we ended with, they slowed it down to 32 meters per second squared, which is about 3 Gs. And it looks like it started about 92, which is about 9 Gs. Okay, so I don't think that roller coasters would subject you to 9 Gs of acceleration. That would be pretty extreme, because in this roller coaster you would basically feel like your body weighed 9 times what its normal weight was, which A little strange to me. So anyway, we get a change of negative 60.